Hello, I'm Ali Shahin Shamsabadi presenting Colorful, Semantic Adversarial Colorization. Adversarial images are intentionally perturbed images that mislead deep neural network classifier. The output of the classifier changed from the suit to the record in this particular example. The LP norm of the adversarial perturbation can be restricted or unrestricted. Robustness and transferability of the restricted ones are limited. However, unrestricted adversarial images are severely distorted with unnatural colors. We propose a black box unrestricted content-based adversarial attack that also exploits human visual system to generate natural color adversarial images. Colorful generate any size natural color adversarial images. Thank you. You can enhance your image while fooling deep learning. Have you ever knew that? So let's talk today about how you can do it using our work called HFool, an adversarial image enhancement filter. By the way, hi, my name is Ali Shahin Shamsabadi, and this is a collaborative work with Sanchez and Andrea. In this talk, we are looking at deep neural networks for image classification, and then we look at how we can fool these deep neural networks. For doing that, first we need to see that how they work. We take an image, and each image is represented by multiple pixel values between 0 and 255. We feed this image through the deep neural networks, or DNN, and the output is the label of the image which we want to recognize. And we train deep neural networks on training dataset consisting pairs of images and labels. So, what is an adversarial image? Adversarial image is an image which is carefully computed to be misclassified. Here I show you one where we start from the flower pot on the left, and the deep neural networks trained on ImageNet is able to recognize it as it is a flower pot. But if we add this carefully computed perturbation in the middle with the image in the left side, we get an image in the right side that human says it is flower pot as well. But when you present the image in the right side to the deep neural network, they recognize this image of flower pot as being a trash can. Adversarial images should have three main properties. Unnoticeability. The adversarial perturbation shouldn't distort the visual quality of the images. Transferability. The property of the transferability is the success rate of the adversarial images in misleading unseen classifiers. The transferability property is satisfied when adversarial images developed for a particular scene classifier is also effective against other unseen classifiers. And finally, undetectability. We compare the DNN's prediction on an image and with its prediction on the image after excusing. In this case, we are following this work and use median smoothing and the quantization as a excuser. If the image and the excuse image produce substantially different output from the deep neural network, the input is likely to be adversarial. So when we design our adversarial attack, we need to consider these three properties in our design. By looking at the literature, one type of the adversarial attack is the constraint one. Constraint adversarial perturbation are generated by controlling an LP norm, for example, fast gradient sign method or FGSM, restrain the maximum change of each pixel. Deepful and CW bound the maximum energy change. And sparseful controls the maximum number of perturbed pixels. As you can see in the images in the bottom right, Most of them, except sparseful, they produce unnoticeable perturbation, while they are not transferable because they are small and overfit to a particular one classifier. In addition to this, constraint perturbation often have high spatial frequency that can be detected by defenses. Instead, on constraint attacks, arbitrary perturb pixels value. For example, semantic adversarial, arbitrarily change the color of the image by randomly shifting the hue and saturation component in the HSV color space. This large and low frequency perturbation in this slide improve the transferability and undetectability of the unconstrained adversarial images in compared to the constrained ones. However, as you can see in the three images in the bottom right, unconstrained adversarial images may be severely distorted by unnatural colors. So in this work, we propose employing an image enhancement filter to generate adversarial images with the objective of reducing detectability, reducing noticeability, and improving the transferability. We achieved these three challenging objectives with a structure-aware adversarial perturbation that enhance the image details or edge, as you can see in these four examples. The proposed image enhancement filter, which we call edgeful, can be used to protect the visual content of your shared photo on the social media, such as Instagram, from undesirable and automatic inference of the classifiers that are located in their platform. To be able to selectively and adversarially enhance the detail, we decompose the image into its structural component. As you can see, the structural component contains the smooth region and the image detail, which is correspond to the edges. And we do this by training a fully convolutional neural network or FCNN with an image smoothing loss function LS. LS measures the difference between the learned structure, IS, and the structure outputted by an L0 image smoothing filter. We then avoid changing the color of the input image and enhance the L channel of the image details. Only L channel of the image detail. After we convert the image from the RGB space to the LAB color space. The detail enhanced adversarial image, finally, the one in the bottom right, I dot, generated by combining the enhanced detail, the L channel of the enhanced detail, with the A and B channel of the original image. A and B channel are the color channel. And then we transfer the resulting image back to the RGB space. To guide the enhancement in an adversarial manner, we use this adversarial loss function that we borrow from the CW work. The adversarial loss LA quantifies the difference between the scores of the adversarial image, which is here I dot, belonging to the same class as the original image, I, and the maximum score among other classes. So it wants to make the adversarial image to go away from the original class. We iteratively train the whole pipeline end to end by minimizing the total loss function, which is the addition of the smoothing loss, LS, and adversarial loss, LA. And then by training this, we are able to generate perturbation that enhance the details. As you can see in the image bottom right, the details are enhanced. We preserve the structure and we maintain the original color of the image. Regarding the experiment, we use two datasets, a commonly used object classification dataset called ImageNet, as well as a privacy-sensitive scene classification dataset called Places 365. And we conduct an attack on two different state-of-the-art architecture of the deep neural network. Residual network with 50 and 18 layers, and AlexNet. We compare our proposed method with 6 state-of-the-art adversarial attack, non-targeted FGSM, targeted private FGSM, deepful, sparseful, CW, and semantic adversarial. As a performance measures, we consider the misleading rate, transferability, and detectability. The misleading rate is the ratio between the number of adversarial images that successfully mislead a classifier and the total number of the images. Transferability is the misleading rate of the adversarial image on a classifier that is different from the one that was used to generate the perturbation. And finally, the detectability is the ratio between the number of detected adversarial image and the total number of the images. An image is detected as adversarial if the L1 distance between the class prediction of the image and the excused image exceeded threshold. And this threshold is learned based on the original images inside the training set. In this slide, we visualize some sample of the adversarial images. As you can see, semantic adversarial severely distort the adversarial images as the color changes are random. A sparseful perturb only a few pixels, but with large and prominent changes that are visible. However, edgeful adversarial images contain perturbation which enhance the detail. I would like to say that we invent a new way of visualizing misleading rate and transferability together. These are the important results of the adversarial attack. As you can see, the top red circle shows the misleading rate against the classifier that adversarial images are generated for. In this case, is ResNet 50. While the bottom orange and green circle indicate the transferability to other unseen classifiers, which are ResNet 18 and AlexNet in this case. If you look at the top red circle, you can see that all adversarial attacks such as FGSM, PFGSM, deepful, sparseful, CW, semantic adversarial, as well as our proposed attack edgeful, successfully mislead a particular classifier, while only 2 of them, edgeful and semantic adversarial, are transferable because of the large perturbation that they are introducing. Excusers such as quantization and smoothing can detect a small but high spatial frequency perturbation of constraint attack, especially PFGSM and CW, that if you look at the values inside the red circle, you can see that PFGSM and CW are detectable by more than 98%. Edgeful is less detectable than constraint attack, but more detectable than semantic adversarial attack, because some of the enhanced details are smoothed out by excusers. Okay, we propose edgeful, an adversarial image enhancement filter that trains a multitask fully convolutional neural network to generate adversarial images whose details are enhanced. By doing experiment on 2 datasets and 3 state-of-the-art deep neural network, we showed that edgeful satisfies misleading, transferability, and undetectability objective. And we also invented a new plot for showing the transferability of the adversarial attack. And we hope by using our method, edgeful, you can protect your privacy when you are sharing your photo in the social media with your friend. Thanks for your attention.